Okay, so let's start. Good morning, everyone. So today we will have a lecture about the introduction to nuclear medicine course. And then for this first course, we will discuss about the diagnostic of cancer. And then, yeah, before we start, let me introduce myself. My name is Deni Hardiansyah, and I'm one of the lecturer in the physics department, Universitas Indonesia, especially from Nuclear Medicine Research Group, University of Indonesia. And then this is the schedule for our course. So we're gonna have in total 2 courses. The first one is today. We're gonna discuss about the introduction, and the second part of our course today is about instrumentation in nuclear medicine. So we're gonna discuss about several modalities in nuclear medicine, such as planar, SPECT, and PET imaging. And all of these are related to the diagnostic of cancer. And then in our next meeting, we're gonna discuss about the introduction to internal dosimetry. And then here, we will discuss about the therapy of cancer. Okay, so let's start with the introduction. So if we're talking about a nuclear application, would you please let me know, maybe one of you, about the application of nuclear? Can anyone tell me the example? Hello? Oh, bomb. Okay. Yeah, Chia, Zaki.
Like, doctor, you mean like in the therapy or
In
daily?
any types of application.
Oh,
What is the first word that you have in your mind if you're talking about the nuclear application? Your friend said that it's a bomb. Or how about you? Do you have another another thinking about the first word coming up to your mind about nuclear application? Yeah.
maybe like radioactive something.
Radioactive. Okay, so it's very interesting because most of the time, if I ask the student about the nuclear application, it's always bomb, and it's true actually. So the nuclear, yeah, we can apply it for a bomb. It's completely correct. So it depends on how we use it actually. Yeah, we can use it for good, or we can use it for something bad, like making a bomb and destroy something. But actually, this nuclear application, we have so many types of application. So for example, we can use it for electricity. We can also use it for food preservation, and etc. etc. Yeah. And then especially today, we're gonna discuss about one of the application for the nuclear in health and medicine. The one that working for the application of nuclear, yeah, especially in physics, for the health and medicine, we call it as medical physics area. Or the one working on it, we call them as medical physicists. So based on the International Organization of Medical Physics, what is medical physics? So medical physics is a branch of applied physics pursued by medical physicists that uses physics principle, methods, and technique in practice and research. So what is the main aim of this medical physics? The main aim is how we implement the radiation, yeah, for diagnostic and also the therapy, especially for the cancer. So the ultimate goal of this is to improve human health. And then I think you have heard a couple of imaging modalities, I believe, yeah, because it's quite famous. For example, like CT scan, and then MRI, and then ultrasound, SPECT, and also PET. So we can see here that there are so many types of imaging modalities that we can use for this application of physics, yeah, in medicine. But the question is, why do we need different types of imaging devices? Anyone maybe know the answer?
Maybe like different technique, different step.
Yes, Ziki, can you repeat again?
They have like different type of method to
Okay, different types of method. Very interesting. Other student, maybe you have any other
Hello.
opinion? Yes, Hasif, please.
Maybe because different part of body scan different, slightly different.
Okay, okay. How we scan the body are different, yeah. So all of the answer are correct. And then if we collect all the answer, then we're gonna have this. Yeah, this is the overview. So we're gonna have this table. So as you can see here, we have ultrasound, we have magnetic imaging, we have X-ray and nuclear medicine. The one that we're gonna discuss today is nuclear medicine. And then here, the measurement principle for each of the modalities are shown here. Yeah. For example, for the ultrasound, so the measurement principle is we use acoustic wave. So this one, yeah. If you want to see the baby inside of the women, then we can use this application. The measurement principle is basically we have a wave, acoustic wave, and then we're gonna measure the information about the reflection, scatter, and refraction at the interface. So you know that when we use the modalities, so we're gonna have the wave that passing through different interface, yeah. So for this, we can get all of this information with physics. We can calculate how the waves are reflected, scattered, and refracted. Then here we can calculate everything to make an image. Okay. For the nuclear magnetic imaging, so what we measure is actually the static external magnetic field. So the alignment of the nuclear spins, excitation of spin by high frequency pulse. We're gonna use a very high frequency pulse, yeah, and then we can have the result of the measurement from the alignment of the nuclear spin. And then we can also measure the relaxation time and also the spin density. For the X-ray, we send the radiation from the outside. This is what we call as the transmission radiation. So we have a machine that can create radiation, and then we're gonna have transmission, yeah, of this radiation passing through the patient body. And then of course, because in the patient body, you can imagine that we have different part of tissue. So this radiation will get some attenuation. And then we can calculate the attenuated beam, yeah, using a detector outside. Then we can make an image out of that. And then for the nuclear medicine, so basically we inject a radioactively labeled compound. And then here we're gonna have the source inside of the patient body actually. So it will move through the bloodstreams, and then it will go to different organs and also, of course, the tumor, yeah, if there is a tumor. And then after that, then this source will create a radiation, and then we can detect it from the outside using a detector. And then what we detect is the radiation of gamma, yeah, due to the decay again that happen inside of the patient body, and then we can detect it from the outside. And then this is what we call as the emission. And then the time scale for the measurement are different. For the ultrasound is quite fast, only within a second. And then for the nuclear magnetic imaging within a minute. X-ray very fast, within a second as well. But for nuclear medicine, yeah, it's quite long, it's around second, minute, even an hour. And then one of the interesting things that we can see here is the resolution. So of course, if you have, for example, like a TV, right, in your home, of course, if we have an option, so you will choose definitely a TV with a very high resolution, right? For example, like a 4K TV, for example, a 4K TV is better than a standard TV, for example. So therefore, if we can see here, the resolution smaller is better. So you can see for the ultrasound, the resolution is around 1 millimeter. Nuclear magnetic imaging is 0.2 millimeter. X-ray is 0.2 millimeter as well, around, yeah. This is not an exact number, but it's around this number. And then for the nuclear medicine, actually, we can say that the resolution is very, very bad, at least compared to other types of imaging method. So it is around 0.4 to 1 centimeter. And then the measured quantity is here again for the ultrasound is the interface, or in the end from the image we can get the information of the morphology. For the nuclear magnetic imaging, we can get the information about the spin density and the relaxation time. And then for the X-ray, we can get the information about the electron density and also the morphology. And for the nuclear medicine, it is not written yet here. But I would like to ask you actually, because you can imagine again, if you have a very good TV with a very good resolution, of course, you will choose that, right? Compared to the other. But why we still having this nuclear medicine everywhere? I think in most of the hospital in Indonesia, we have nuclear medicine facility. Even though it's not all hospital, they have a complete modality, but I believe that some of them, yeah, having this nuclear medicine modality. But the problem is, again, the resolution is not that good compared to the other, but why we still need it? Anyone maybe have some comment for this? Have you heard nuclear medicine before at all? Maybe you know about this, and maybe you can have an idea why nuclear medicine is still important and we have it in many hospitals. I think that in Malaysia we also have a lot of nuclear medicine facility. Yeah, Jackie, please.
Maybe due to lower cost.
Lower cost. Okay, thank you, Jackie. Other student, maybe do you have any comment for this? Okay, no, so I'll continue that. So about the cost, unfortunately, nuclear medicine is quite expensive compared to the other. Sometimes nuclear medicine is more expensive than the other. But I will give you one word, very, very important word for the nuclear medicine. Functional imaging. So what is the meaning of functional imaging? This is the one that we will discuss today. Yeah, why the nuclear medicine department is very important in the hospital, and why we need it compared to the other also, because the other is sometimes cheaper and then also better in the term of the quality of the image, but still we need it because of this actually, because the functional ability, yeah, to show the functional of an organ or the tumor. So we'll discuss this further. So anatomical versus functional. So as you can see, we have two set of image. On the left side, you can see several images from anatomical imaging. And on the right side, we can see the functional imaging. So what is the meaning of anatomical and functional imaging actually? So we will discuss it first for the MRI. MRI is very good for soft tissue actually. So we can see, as you can directly see here, yeah, how we can see the brain is very, very nice. We can see all things about the brain here, I think, and all other things as well. We can see salivary gland and everything, yeah. And then for the CT, we can also see the difference between soft and hard tissue. Yeah, even the cigarette, we can see it here, right? The ultrasound as well, and also angiography if we would like to see the branch of the blood vessel. So it's very good. So anatomy information, we can get it from this modality. But for functional imaging, it is more related to the function of an organ. So you can imagine, because we inject the radiopharmaceutical drugs inside of the patient body through the bloodstream. So of course, you can imagine that how this drug moving to the organ, yeah, getting into the organ and coming out of the organ, we can really see how fast or how slow they are. So therefore, we can really see whether, for example, if we're talking about, let's say, one of the example is the kidney, for example. I have several examples in the next slide, so we can discuss further. But in brief, you can imagine that if we have a kidney from two different patients, yeah, we can really distinguish the function of the kidney for these two patients. Maybe patient number one, the kidney is still very good, yeah, walking nicely and so on. But for the second one, the kidney is not very good, for example. We can detect that. We can see that from the functional imaging. Yeah, we can see how fast they moving into the organ, in this case kidney, how fast they are cleared from the kidney and so on. So this is one of the example of the functional imaging. We can use what we call as the positron emission tomography. And then this is one of the example of the image from functional imaging. In this case, we use positron emission tomography. If we use imaging with glucose metabolism, we have two images from two different patients. Yeah, on the left side, we can see that this result is for the normal volunteer, for example. On the right side, we have Parkinson's disease. So we can see, you see, if we have a bright color, it means that we have many radiopharmaceutical drugs inside of this area. And it means that we have an activity of this part of the brain from this subject with a good result, we can say. Then we can say that this is a normal, normal volunteer. But for this, no, you see, the activity is, much smaller, yeah, compared to this. And then from this, then the doctor can say, okay, there is something wrong with this subject. And then we can say that this subject has a Parkinson's disease. And then we can also see the function of the heart, for example, yeah, using positron emission tomography or single photon emission compute tomography, PET or SPECT. And as you can see here, during the stress time and also the rest time, we can see different functional of the heart. Yeah. You see, for the rest, we have many color here. For the stress, we have less and so on. And we can also do the same for the tumor. So by using functional imaging in nuclear medicine, we can say that, okay, this tumor is already very bad. And then it's already in stadium number 4, for example, or in stadium number 1, or stadium number 2, or etc. Then we can define it using functional imaging. So this is the reason why, even though the image is not that good, as you can see here, the image is very, very nice, right, in the term of the resolution. But on the right side, you see the resolution is not that good, right, compared to this at least. But still, we still need it, because from all of these imaging modalities, information that we can get is the anatomical information. But from here, we can get different types of information. In this case, the functional information. So therefore, still the nuclear medicine department is important in the hospital, okay? To see the function of the tumor and also the function of the healthy organ. So the question is, when using image in medical imaging and in radiotherapy, we have a question, what are all the different questions you want to get answer from the image? Especially for the imaging, we have the question, what is it? And for the radiotherapy, for the therapy, we have a question of where is it? So by definition, what is nuclear medicine? Nuclear medicine is a topic where we apply the radioactive or radioactively labeled substance for diagnostic or therapy of a cancer. So main field of application itself, first for the functional diagnostic of internal organs and tumor as well, detection or localization of tumors or of inflammation sites. And then the last one is we can also perform molecular radiotherapy or targeted radionuclide therapy. So you can imagine, let's say that we have a patient, right? And then sometimes we do not know, we cannot see sometimes if there is a tumor in certain part of a patient body, because let's say that the uptake of the tumor is not very good, the oxygen level of the tumor is not very good, so it is very difficult to see the tumor, and the tumor in addition is small, so it's very difficult to see the tumor. But you can imagine if we inject this radiopharmaceutical drugs inside of the patient body, then you can imagine that these radiopharmaceutical drugs can tracking down the tumor. So even though we cannot see it from the image, then we can make sure that these radiopharmaceutical drugs will get into the tumor. Even though you can imagine that it's very it is a very dangerous, right? Actually, because we add this radioactive substance to the patient body. It's very dangerous actually. So that's why in physics this is very important. Your experience in calculating the dose, for example, to make sure that even though it is very dangerous, because it can kill the patient, because it is a radioactive substance, can create radiation. But if you are a good physicist in medicine, then you can calculate it to make sure that, okay, this radioactive substance will help us to treat the tumor, but won't make any bad effect to the healthy organ. So you can imagine again, this is one of the applications of physics, that showing the importance of physics, at least in medical field. So as a physics, you need to be proud. Okay, so we can continue. This is a small video about the introduction to nuclear medicine. So what is nuclear medicine? So we can discuss about diagnostic and therapy as well, And then, for example, we have a patient, and then the doctor would like to see what happened inside of the patient body. So then we first take the patient to the nuclear medicine department, and we inject the radio-labeled substance inside, and then it will move to the target sites, in this case to tumor, And then we scan it. So the detector is located outside of the patient body, And then we're gonna have this information of the functional imaging from PET, for example. And then we scan it again. We can also get the information from the CT. I'm sorry, the first one is the CT, the second one is the PET. And then after that, we can also have the opportunity to fuse it. Then after that, the doctor will check it, and then can diagnose better whether the patient having some disease or not, and in which level, and so on. And then for the application itself, there are a broad application for the nuclear medicine, And then, this is the main mechanism. It will concentrate in the disease and then destroy the disease, for the therapy. That is the main aim. And then for the personalized medicine itself, we can have many applications in neurology, in cardiology, in oncology, in orthopedic, yeah. So there are so many applications of the nuclear medicine. But actually, it is similar like, I'll say, a drug that you can get from the pharmacy. So let's say that you have a problem with your head, right? You have a headache, for example. And then, of course, you will go to a store, a pharmacy store, and buy a drug, of course, specifically for your headache, right? And then how can you believe that that drug won't go anywhere? So that is the same question that we can answer here, actually, because this drug can target a specific things inside of the target sites. For example, in this case, the tumor. So of course, if we have a headache, then we are sure and we believe that the drug that we take from the pharmacy store will go just to fix the problem inside of your head. Okay. And then if you have a stomachache, you're gonna have different types of drug, right? It is nonsense if you take also the headache drug to solve the problem of your stomachache. Okay. So this is similar with nuclear medicine, actually. So you're gonna have different types of drug that can solve different problems, and also can help you to diagnose different types of tumor. Yeah. So for example, yeah, if we would like to see which one, then we're gonna have certain types of drug that can help us to get our aim to diagnose something inside of the patient body. Okay. So it is very specific. So again, maybe again, I believe that in your mind, you can think that this is very dangerous, but don't worry, because it is similar like your headache again. Even though you know that this drug, you take it orally, right? You put it in your mouth and so on. So how can you believe that it will just go to your head? But it is really going to your head and solving the problem of your head, right? So it is also similar with this. So it will go to the target that we want only. Okay. So the journey for the radiopharmaceutical itself, yeah, first we have a production of the radioactive compound. It can be from the reactor or the cyclotron, and then after that we label it, yeah, with the drugs, and then we take it to the hospital. Okay. So in the hospital, we need to have this facility, yeah, of the radiopharmaceutical drug production. So what we inject actually, yeah, what we inject to the patient body. So what we inject is this one, a set of 3 different things. The first one is the drug itself. One of the example of the drug is the peptide. The second one is the chelator, and the third one is the radioisotope. Yeah, and then if we explain it one by one, this is what we inject to the patient, the radiopharmaceutical drugs, or we can say a labeled drugs that can target and irradiate the tumor. Contains, the first one is the pharmaceutical drugs. This drug can target a specific feature in the tumor sites. And then this is, again, how it works is similar with the one that you have from the drugstore. Okay. And then the second one is the chelator. The chelator is actually just a chemical materials that holds drug and radionuclide together. And then the last one is the radioisotope. This one is just an unstable atomic nucleus that can generate gamma, beta, and alpha radiation. So let's discuss this one by one. Yeah. So again, by the way, you know that in our life, we cannot solve all the problems, right? As a physicist, we can only solve the one that related to physics. So for example, the medical doctor, they cannot calculate, for example, exactly the absorbed dose, the radiation absorbed dose. Yeah, because it is related to physics concept. But for this one, we cannot also do it because this is related to chemistry. So for this, and also the pharmacy school, of course, they're also working for this. So for this, as a medical physicist, especially the one that working in the hospital, we directly get this as a product, yeah, of the radiopharmaceutical drugs. The one that creating this tree and then making it all together into one, yeah, it is not our job. Okay, it is the job of the pharmacy people or chemist people. So let's discuss one by one. What is the radionuclide? Yeah. Can you hear the sound of my video? Anyone? Can you confirm?
Yes.
Oh, you can hear. Okay, good. Very good.
No, sir, sorry, I can't hear the videos.
Jackie, you can hear the sound of my video or not?
No.
No, okay. Okay, there was a misunderstanding then. So let me stop my share and then redo the sharing with the sound. Okay, now it's good one.
Oh, yeah.
Now you can hear.
Yeah.
Okay, okay, okay.
Okay, thank you.
How do you know if an atom is stable? In this video, we're going to learn about radioactive decay. An atom is composed of subatomic particles called protons, neutrons, and electrons. Positively charged protons and neutrons with no charge from the central nucleus. Negatively charged electrons orbit the nucleus. For more information on atomic structure, watch this video. A strong nuclear force holds the positive protons and neutral neutrons together in the nucleus, and is what determines if a nucleus is stable. In stable nuclei, the force is strong enough and brings sufficient energy to hold the nucleus together permanently. Most of the nuclei formed during the Big Bang nearly 14 billion years ago are still in existence today. But not all nuclei are stable. Unstable nuclei either have too many protons or too many neutrons, upsetting the strong nuclear forces. Unstable nuclei try to balance themselves by giving off the excess proton or neutron. This is radioactive decay. Unstable nuclei are radioactive and emit radiation. There are three types of decay: alpha decay, beta decay minus, or beta decay plus. Alpha decay is the loss of an alpha particle. An alpha particle is made of 2 neutrons and 2 protons. They have a mass of 4 and a charge of +2. When an atom loses an alpha particle, the mass number decreases by 4 and the atomic number decreases by 2. A new element is formed that is 2 places lower in the periodic table. When an isotope has too many neutrons, it decays by beta minus decay. A neutron changes into a proton and an electron. The proton is retained by the atom, while the electron is lost. The lost electron is high energy and is called a beta particle. By losing a neutron whilst gaining a proton, the mass number of the atom remains the same, but the atomic number increases by 1. A new element is formed that is 1 place higher in the periodic table. When an isotope has too many protons, it decays by beta plus decay. A proton is converted into a neutron and a positive beta particle called a positron. Positrons have the same mass as electrons, but the opposite charge. By losing a proton but gaining a neutron means the mass number stays the same, but the loss of a proton means the atomic number decreases by 1. So how do we know if an atom is stable or unstable? We can determine whether a radioisotope is likely to decay and what type of decay is likely to occur by looking at its position on a proton-neutron NZ graph. This graph shows the number of protons on the x-axis and the number of neutrons on the y-axis. This is the stability line. If a radioisotope lies left or right of this line, it is unstable and likely to decay to become stable. A radioisotope that lies to the left of the stability line has too many neutrons and is likely to undergo beta- decay, so give off electrons. A radioisotope that lies to the right of the stability line has too many protons and is likely to undergo beta+ decay, so give off positrons. If particles have a high number of protons, usually more than 82, they are likely to undergo alpha decay. In this video, we have learned that unstable nuclei either have too many protons or too many neutrons, which upsets the strong nuclear force holding the atom together. Unstable nuclei try to balance themselves by giving off the excess proton or neutron either through alpha, beta- or beta+ decay.
Yeah, so that is the type of radionuclide that we use in nuclear medicine. Yeah, whether we can use the alpha particle emitting radionuclide or beta- or beta+ emitting radionuclide. Yeah, so this is just a basic physics, so at least we can try to remember a couple of important topic that could lead us to a better understanding in nuclear medicine. So the next one is, let's discuss about the pharmaceutical drugs. What is pharmaceutical drugs? It seems like there is no sound here, so I'll just explain it. Yeah. So, okay, let's say that we check a patient, right? And we would like to make the patient healthy again. How we can do that so that they can improve the quality of their life. So then we need a drug, of course. Yeah, that effective and also safe. And then, yeah, the step that we need to do is the target discovery. So in this part, we have a sample of our disease. For example, let's say we're talking about the COVID-19, for example. So we can get the sample from the COVID-19, and then the researcher in the lab, they will check the feature, yeah, of this problem. In this case, COVID-19, for example. And then they will try to check what we can target. Yeah, you see here, because we can get so many part of the target, but we're gonna find the most optimal one, the one that can also make a chain reaction to solve the problem. Yeah. Okay. So if we have this chain reaction, that's gonna be very, very good because it can make the drug very effective. So we need to find these types of drug. Okay. So because we already know the target in our target site, yeah. And then of course the next step is how we get the drug. Yeah. And then to get the drug, then we need to move to the second step, the drug discovery. So we can do it in our lab and also in our computer to find different structure of the chemical element to make one molecule, for example. And then we check more than 10,000 structure here in our computer and also checking it in our lab. let's say that we have several candidates here, and then we're gonna test it to this target that we have from the tumor, for example, or from the COVID-19 cell. And then after we test it, hopefully we can solve the problem that we have. Yeah, the most important thing is we need to make sure that our drug is safe and also effective. And modification of the drug can also happen in between to make sure that these two aims are met. Okay. So it takes a very long time actually to develop a drug, and take a lot of money, can be up to $2 billion. And then you can imagine from more than 10,000 candidates, we're gonna have only one that go into the market. And the time is quite long. Yeah, for one drug takes about 11, 12, or even 15 years. And then we also needed to test it to the subject, to the living subject, in this case the patient, to see the effect. Yeah, whether the effect is good or not, as expected or not. Yeah, but first before we go to the human, we need to test it in animals, because the first thing that very important is to make sure that our drug is safe. So we test it in mice, for example. Yeah, we inject it with this drug, and then we also need to check it with our government rule, whether our protocol is accepted or not. And then after we test in animal and we found that the drug is safe and also have a high efficacy, then we can try it in human as well. We hope that we can decrease the number of the animals, because at some point we need to kill the animal, right? And it's not good. So nowadays people try to decrease the number of the used animals, or even erase it at all, because right now we can also use some kind of small animal imaging, for example, even though it's very, very expensive. But the point is we try to decrease the number of the human and saving the lives. Okay. Yeah, okay, so we have the drug, we test it, and then we're gonna need to do some refinement, the reduction, and also replacement, to make it optimal. And then we're gonna go to the human clinical phase. At least we have 3 phases here to make sure that our drug is safe and also effective. And this one is from the US, so you can check it here, for example, information about this clinical study. So in the first step, we check this drug in healthy volunteer, because the most important part of drug testing is we need to make sure that they are safe. So we test with a small number of sample from normal volunteer, and then we test it to them to see whether it's safe. Okay. And then after that, we are sure that they are safe enough. Then we test it with a larger sample size of the volunteer, also can be for the patient, to see also the efficacy. Okay. So we need to make sure that it is effective. And then we can also check it with different types of drug here. I mean, you know that you are creating and developing a new drug, right? And of course, you need to compete with other pharmaceutical company. Then you need to also show to the government body working for this drug development that your drug is better than other types of drug out there from other company. If it's not better, then you need to show the evidence why they need to approve it. Okay. And clinical phase here, we can check it even with a very high number of the sample, 1,000 to 3,000, yeah, to see the effectiveness. Again, we need to have some data here, and we can register it to the government and so on. Okay, so you can imagine here that pharmaceutical drugs, we need to make sure before we inject it to the patient, it's already passing a very long and also a very complicated testing. From the first step is the drug discovery. Yeah? We check it in our lab, we check it in animals, we check it in normal volunteer for the clinical trials, and then we check it in patient and so on. So it's already passing a very long, complex and also complicated testing. So after that, then of course, in the end, we believe that this drug can really target the one that we would like to, yeah. So again, we should not worry actually that this drug will go anywhere and make a very bad things to many organs, because it's already been tested, yeah, that it will go mostly to the tumor, for example, in our case, for the cancer. But again, just one note that actually this can also lead to a very bad result if we inject too much. If we have a very high injection of the radiopharmaceutical drugs, then we increase the absorbed dose, the radiation absorbed dose in our organ matrix, then our organ matrix can be destroyed. So this is your job as a medical physicist if you are working here, yeah, in this area, to make sure you need to calculate with the physics, background, yeah, with equation and so on, to make sure that this number of the dose is good enough. So there is a difference between the drug from drugstore and these radiopharmaceutical drugs. Why? Because if you have too many drugs from the drugstore, right? Maybe it can kill you, but the effect won't be that bad compared to the radiopharmaceutical drugs, because we're talking about radiation here. If you are not calculating it carefully, then it can kill the patient. Yeah. So therefore, your role in a hospital is very, very important, and no one can calculate it except the physicist. So you need again to be proud as a physicist. Yeah. Not only for this medical implementation of the physics, but also in different types of implementation of physics. Okay, so this is the historical overview. Yeah, so it started in actually 1896 from Henry Becquerel. He found the radiation from uranium salt, and then in 1923, George von Hevesy found that there is an absorption of lead or a plum in plants. So here, this year is the first time people see that there is a possibility of the radiation, radioactive substance that can be used for human subject. Yeah, and then in 1927, Bloom-Gart-Weiss found the circulation measurement of radium in biological system. In 1927 as well, in the same year, E.O. Lawrence found a cyclotron that can produce isotope. That this one is very, very important for especially the positron emission tomography. And then 10 years later, Hans Robert showing the diagnostic of thyroid. The thyroid cancer can be diagnosed using these radiopharmaceutical drugs. And then in 1947, Kalman showing the detector, how we can detect the radiation inside of the patient body using scintillation crystal. In 1951, Benedict Kesson showing the first rectilinear scanner. Hal O. Anger in 1958, creating gamma camera or Anger camera. And then in 63, 75, 98, and 2008, they found many good modalities that can be used for nuclear medicine. For example, the single photon emission tomography, positron emission tomography, and also the combination of different modalities here. Okay, so that is the last part of our course today, and we'll continue to the instrumentation in nuclear medicine. Before I continue, is there any question for the introduction part, please? Anyone?
Doctor.
Okay. Yeah, please.
Sorry to ask this, but may I know
Yeah.
what historical overview for this? I mean, this slide. What is the historical?
Can you repeat again? I'm sorry, I cannot hear you clearly.
Oh,
Can you repeat again?
may I know for this slide, what is the historical overview for this current slide? Is
Okay.
it
You mean that?
radiotherapy?
Yeah. So in this slide, actually, I would like to show you the history of the nuclear medicine application, especially for a human subject. So you can see here that in 1896, right? So Henry Becquerel, this is the reason why Becquerel, I think this is a very common term for you, right? For radiation. He's the first one showing radiation from uranium. So, and as you can see here, in around 1975 to 2008, the development of this imaging modality is booming. We can see that there are so many new detector and also machine that we can use for the application of nuclear medicine in human subject. Okay, Jackie?
Okay.
Am I answering your question or?
Yeah, you answer.
Okay, thank you.
Thank you, Doctor.
Okay, thank you, Jackie. Is there any other question? Yeah, please.
Can I ask?
Yes, sure.
Yeah, because you said that the nuclear medicine was tested in animals' body.
Yeah.
How do we know that if the reaction between the animal body and also the human body towards the nuclear medicines it is the same? So because due to the different metabolism and also functional of the organ.
Okay, thank you. Thank you very much. A very good question. What is your name? Because I cannot see your name from your Zoom.
I'm Baxter.
I'm Baxter.
Yeah.
Baxter. Okay. Thank you very much, Baxter, for a very nice question. So you're right that actually we are never sure, right? What happened inside of the patient body would be the same with the one that we get before from the characteristic of animals. And that is for sure because we are different species, so the response are different. So therefore, here we need to test it. So you see here that we have these radiopharmaceutical drugs, right? That we use for human. And then these radiopharmaceutical drugs contains of these three types of different molecules. The first one is the drug itself, the chelator, and the radionuclide. We don't have to care about the chelator because the chelator doesn't do anything actually. It is just something like your seat belt. You know, you have a seat belt in your car. So the chelator is the one that making sure that you are not moving anywhere from your seat. So it's similar like that. So this chelator will make this pharmaceutical drug hold together. The drug and radionuclide will move together. Okay, so we just need to care about these pharmaceutical drugs and radionuclide. Okay, so let's discuss one by one. For the pharmaceutical drugs, yeah, first we need to do the drug development process only for the pharmaceutical drugs and make sure that these pharmaceutical drugs can really aim the target in our tumor site. Okay, we need to make sure about that. And then first we also test it in animals, and then after that we test it in human. But before we test it in human, we need to calculate what we call as the first in human dose. Yeah, first in human dose, we calculate it, we translate it from the animal data into human data. And then this number for safety, usually we lower it down up to 10 times or even 100 times. You understand what I mean? So we need to lower it down because safety is always coming first compared to the efficacy in human. Because we also believe that, yeah, human and animals, they have a different characteristic of metabolism and so on, right? So therefore, we need to calculate this first in human dose. And then after that, we lower it down, yeah, 10 times or even 100 times, and then inject it to the normal volunteer for the first step of the clinical study, right? And then, of course, the difference will appears. That is for sure between what we can have from the human and also the animals. And then we need to explain the difference. Okay, if we can explain the difference, then we can move on to the patient. So the patient implementation of the drug is the next step. Yeah, clinical trials number 2, not the clinical trials number 1. Because first, before we test it to the patient, we need to make sure that it is safe. If we lower it down, maybe you have a question. If we lower it down by 10 or 100 times lower, then maybe we cannot see, yeah, the efficacy. It doesn't matter because we need the information of the safety first, right? If it's safe, then we can scale it up. It's not a problem. But you need to understand that we scale it up step by step as well. It doesn't mean that we have one number, we scale it down 10 times, and then we scale up to 10 times higher. No, not like that. We scale it step by step to make sure that it is still safe in each of the steps. Okay? And then after the pharmaceutical drugs has been proven to be a very, very good drugs, and then after that, then we use the radionuclide. So we have this labeling step, yeah, and then after we make sure that this is safe, this one is also having a very good efficacy, then the next one is we test the radionuclide. And then how we test it, we start it again in the animal, and we do the same step one by one, and then we check the radiation from the radionuclide as well. Yeah, so that is the step, Baxter. It takes a very long time and very time consuming, but yeah, you know, human life and also animal life is very, very important. So that's why we need to go through all of this very difficult step to make sure that everything safe and also can give us a good efficacy. So any other question, Baxter, or maybe enough?
Yeah, that's enough. Thank you, Doctor.
Okay, no problem. Thank you very much for the question, Baxter. So I think we can continue, yeah. So after we already know about this history, about all of this machine of the detector, yeah, for the imaging, let's discuss one by one in this instrumentation in nuclear medicine. So the learning objectives are, first, I hope that you can explain the basic component of gamma camera and reproduce the terms of static and dynamic measurements. I hope that you can also explain the term tomographic and describe the principle of SPECT and PET. And also, I hope that you can discuss, yeah, the difference between the SPECT and PET imaging, and also name the different methods of image reconstruction and discuss the differences, including the advantage and also disadvantage. And then this is a note for you that it is definitely not sufficient to just learn from this slide. So you can imagine I give this lecture for the whole semester, you know, and then I give you the diagnostic of a cancer in nuclear medicine in only 2 hours. So of course, it is not sufficient at all. So I suggest you, if you are interested, then you can learn more. Yeah, not only from this slide, but also checking more reference and books. So I'll give you some reference that you can read in the end of my presentation today. Okay, this is the outline for my lecture in instrumentation. So we start with the conventional scintigraphy with the scintillation camera, tomography, single photon emission compute tomography, positron emission tomography, and also image reconstruction. So this is the conventional scintigraphy that we discussed in the first part of the lecture: scintillation camera, tomography, and also SPECT. So in general, let's say that this is your patient, right? And then this is one of the slides from the patient body. And then this is actually your scintillation camera. So the scintillation camera is actually divided into different types of machine. The first one is the collimator. The second one is the crystal, the scintillation crystal, and then the photomultiplier tube array. Okay, and then the principle is, I think, quite straightforward, where you have the radiation from the patient body, and then this radiation will move everywhere, right? And the one that in parallel with the collimator will go through this collimator, and then the crystal will read the signal here, and then they will collect it in the photomultiplier tube, make the signal bigger and higher, because this signal is very, very weak, and then we can read it in our computer. And then if we check it from above, we can see the machine is something like this. Yeah, we have many scintillation camera here. We also have some position logic here to see if we have radiation in number 2, for example, then we're gonna have a certain coordinate of the radiation, because in the end we need to make an image out of this machine, right? Then we need to define the location for each of the radiation inside of the patient body. So we can use this logic, yeah, from detector of photomultiplier tube number 2, for example. Then we can calculate the X in the in this negative X direction, and then in positive Y direction. So we can get the exact location of each of the radiation to make a full map of the radiation from inside of the patient body. So this is the machine. As you can see, yeah, this is a patient here, and then we have actually we have 2 machines here. The first one is on the top part of the patient body, and the second one is on the bottom part of the patient body. And then if we open it, then it's gonna be something like this, yeah. And then this machine will move but no, it depends on what we would like to perform for the measurement. So if we would like to perform a whole body imaging, then this machine, yeah, will move from the head to the lower part of the patient body. So it depends. So if you just want to see what happened around this abdomen part, then it won't move. And then we're gonna have 2 images from these 2 detector, yeah, from this detector and also this detector, yeah. And in the end, we're gonna have this 2-dimensional projection. And then if you open this, we have this machine. So again, this one is the collimator, this one is the crystal, and then this one is the photomultiplier and electronic. And then the principle is how collimator can select the radiation that only parallel to the collimator hole itself. So we don't want to have this black arrow information, because this can really make our image destroyed. So it is like a photo, you know, you would like to see that, let's say we're taking your photo, right? So we would like to see, of course, your nose location in your nose location. You understand what I mean? It doesn't make any sense if you have a photo in your phone, you take a picture of yourself with a selfie, and then you found that your nose is located in your, I don't know, in your body, for example. So we need to delete that kind of information, a very bad information. So this nose, yeah, if we have an image here, this nose should be located only in this part, yeah, not in other parts. So we don't want to have information from the nose here, for example, yeah. So we need to use this collimator. And then wait, could you please wait for 1 minute? I'm sorry, let's continue. So this is the machine, yeah, the real machine of the gamma gamma camera head, if you open it. So you can see here, yeah, this is the crystal. We cannot see the crystal. We need to open this. But at least you can see that all of these are the photo multiplayer tube, yeah, and then we have a lot, actually. And then we can image it, yeah. And then one of the job from medical physicists working in hospital is also checking, for example, the uniformity. So we need to make sure that the signal from each of the detector are uniform. You know, for example, this one doesn't look very uniform in my opinion. So you can see these two results. On the left side, it looks very nice, and on the right side, seems like yeah, it's not a very uniform. And this is your job if you work in for a hospital, working for the nuclear medicine department. Yeah, this is one of the jobs. And then this is another picture if you would like to see more picture of the photomultiplier tube. Yeah, so you see here we have many tube here, and then we have some electronics here. Yeah, okay. Okay, let's see some video here. I'm not sure whether we have some. Oh, there is no song. So I will explain it then. So here we will discuss about the component of the gamma camera. Yeah. So this is the machine. And then, yeah, basically, let's say that we already inject the patient. Yeah, patient has a radioactive tracer inside them. And then the gamma ray are emitted to all direction. And in this gamma camera, it will detect the gamma ray and the location of the radionuclide display on the monitor. And then here, if we open it, then we're gonna have a component, at least 4 main components in the gamma camera. The first one is the collimator. The second one is the scintillator. Yeah. The third one is the photomultiplier tubes. And then the last one is the computer or electronics. Yeah. Okay, let's discuss one by one. The collimator. So the shape of the collimator is similar like the honeybee, like this. Yeah. And then there are parallel lid tubes. Yeah, it's hexagonal. And the lid, the blue one, can absorb, yeah, the radiation. So you can imagine if we do not have this collimator, then any kind of radiation, even though a very bad radiation with wrong information, can also be read, yeah, with the red one. But with the collimator, we can select only the important one can move on to the scintillator part of the gamma camera, yeah, and the other one can be absorbed. The red one can be absorbed by the collimator, and then we can see the origin of the detected rays in a good way. Okay. And this is the scintillator after passing through the collimator. Yeah, the radiation will move, the gamma radiation will move to this scintillator. So how it works actually? So the incoming gamma photon will change into the visible photon by the scintillator. Okay. Okay, so we're gonna have more signal as well here. Many visible photon from one gamma photon. And this gamma photon produce a tiny flash of light. And then after that, we will move to the photomultiplier. So photomultiplier will increase, yeah, the signal. And then you see this will create an electron path, and then it will move to different dynode, and it will get into, I mean, it will create more and more electron. And then in anode, then we're gonna have a cascade of many electrons, and we're gonna have a better signal because the first signal is very, very weak usually. And then from the computer, we can have all the signal all together, and then we can analyze it in our computer to get the image of the distribution of the radiopharmaceutical drugs inside of the patient body. Yeah, so that's it. Yeah, so in general, the gamma camera is consists of a collimator, scintillator, photomultiplier tubes, and also the computer. In collimator, define gamma location. Yeah, in scintillator, changing the gamma to visible light. For the photomultiplier, visible to electronic, and computer processing the signal. Okay. So this is one of the example of the measured energy spectrum. In the x-axis, you can see the energy. Yeah. And the y-axis is the impulse. And then you see this is the example, one of the example from iodine 131. Yeah, and then the distribution of the energy is not something like only having one jump, but we have several jump here. But the most important one is, for example, for the I-131 is 364 kiloelectron volt for the peak. Okay. And then this is one of the other job for you as well if you're working as a medical physicist in a hospital. So as a medical physicist, you need to help the doctor to get a good image. For example, on the left side, if you performing your job very well, then you can get this appropriate energy window, then you can get this very nice result of the image. But with the same signal, if you working bad as a medical physicist in a hospital, then you set a wrong window, then you can have a very bad image. You cannot see anything, right? And you must understand again that this job is only belong to you as a medical physicist. So you need to learn good enough to understand everything, because it's very difficult for the doctor to read the diagnostic of this image, right? Because you cannot see anything here. So therefore, your job in the hospital as a medical physicist is very, very important. By choosing an appropriate energy window, then you can have a very good image that can be read by the doctor. Yeah. Okay. So again, we already discussed about this, and then the term of dynamic and static, you also need to understand it. Yeah. For example, for the whole body scintigraphy, so it means that you take the image of this patient from the head to the lower part of this patient body. This is one of the examples from the radio pharmaceutical drugs of PC99M MIBG. Yeah, and as you can see here, we can see some organ arteries. Yeah, This one is the liver, this one is the kidney, and etc. This one is the bladder, and then all of the other dot is for the tumor. So unfortunately, this patient has so many tumors, yeah, and it's already, yeah, everywhere. It's already everywhere. And then that is the static measurement. It means that you measure the patient body just at one time point after the injection. Okay, that is what we call as the static measurement. But for the dynamic measurement, so for example, we inject these radiopharmaceutical drugs, TC99M-DTPA, yeah, these radiopharmaceutical drugs, we can use it to explain, yeah, the function of your kidney, for example. We inject this, sorry. We inject this to the patient body, and then after that, we perform the measurement with our detector several times. For example, we measure from 10 seconds to 20 seconds after the injection, we get this image. We measure 20 seconds to 30 seconds, we get this image, and so on, so on, so on. So in the end, we're going to have many images. Yeah, this is what we call as the dynamic measurement. So we have information about the image, functional image for different imaging at different time point. Again, this is what we call as the dynamic measurement. And then after you get this image, this is your job as well, okay? Functional imaging, it means that you would like to see the function of the organ or the tumor, right? And how we can get the functional information. To get the functional information, you need to extract the quantitative information from each of your image. For example, let's say that you take one of the image from this serial set of the image, right? And then the next step is you need to make a ROI, the region of interest of these two kidney, because you know that for human we have two kidneys, right, on the left and on the right side. So we make this, and then who create this? As a medical physicist, you need to do that. And then after that, you also need the background. Yeah, you make this two background, for example. And then after that, you can get the information of the pixel value for each of the region of interest. In this case, two region of interest. Yeah. And then from this pixel value of the region of interest, you can convert it, yeah, into the activity. How to do that? Then you need to learn. If you're working for a hospital, then you need to learn how to convert the information of the pixel value into the activity information. Yeah, and then in the end, you're gonna have this curve. On the x-axis is the time. On the y-axis is the count rate. For example, in this case, we have a count per minute divided by the megabecquerel. The pixel value here is the count. One count is one radiation. Yeah, one radiation recorded in your detector. So count per minute, it means that how many radiation per minute of time that you get from your region of interest. And then after that, you can divide it by the megabecquerel because you have the calibration factor. In this case, yeah, you first inject the patient with 100 megabecquerel of the activity. And then you can get this curve. You can imagine that the right kidney is the red one. The left side is the black one. Yeah. And then one dot corresponds to one image. So if you can get so many dots like this, it means that you have so many images. Okay. And then after that, if we zoom in this part, then you're going to have this part. Then let's read what we can get here from this curve. Yeah. After you make the ROI, and then after you get the information of the activity, or in this case, the count rate, yeah, from this pixel value, then you're going to have this. And then after you have this, what we can get from this? So first of all, you see, at time 0, we don't have any radiopharmaceutical drugs inside of our kidney. Yeah, it's logic. Why? Because to inject the radiopharmaceutical drugs to the bloodstream, to the vein, yeah, okay, of the patient. So of course you cannot get any information at time 0. And then after that, you see that these radiopharmaceutical drugs increase so fast, and then moving in to the kidney, and then after that it decrease, yeah, decrease over the time. And then if you see here how these two different kidney are working are different. So it seems like you can see the right side of the kidney working harder than the left side, because it can get more radiopharmaceutical drugs, and then they have, yeah, most of the time, I think, right, for the radiopharmaceutical drugs inside of this right kidney compared to the left one. So it means that we can say again, the function of the right kidney, they function harder than the left side. So this is actually one of the reason or the meaning of the functional imaging. By having this functional imaging from the patient, we can really get information about how right and left kidney are working. Okay. For example, in here we can also see that right kidney working 61% and left kidney working 39%. Yeah. So the right kidney is working harder. So we can see again the function of the right and left kidney by using this nuclear medicine, and it is very beneficial. So I'll show you another example. So we have another patient, right? And then from this patient, we also perform many dynamic measurement, yeah. And then after that, we make the ROI. By the way, you can see that on the left side, yeah, we have a larger ROI than the color itself. Why? Because you need to remember that we cannot get the anatomical or the volume information from nuclear medicine. So this ROI, we get it from the CT scan actually, because we can get the information of the volume from the CT scan, right? So we can create this ROI, we can also create this ROI, and then we can calculate the pixel value, and then we can convert the pixel value, yeah, to the Conrad, and then you can see here the right side working very hard compared to the left one. Okay, and if we calculate the uptake, then we're gonna have the right side working 87% compared to the left side. It means that for this patient, the left side kidney is almost destroyed. It's not working properly anymore. So here again, this is the meaning of the function. By having functional information from this nuclear medicine, we can see that for this patient, there is something wrong for the left side. This one, okay, yeah, the left side is not working harder than the right side of the kidney, but still they are almost, I mean, similar, right? But this one, it's almost, we can almost say that the left kidney is, I mean, almost destroyed or not working properly at all. You know that for human, we can live with only one kidney, right? So therefore, this patient can live with only the right kidney. But this is not good, because then we force this kidney to work harder, yeah, compared to other normal people. Then we can also do this similar things for the tumor. You can imagine. So we can see the information of the tumor by performing this type of measurement. We can say that, okay, this tumor is very, very bad. It's already everywhere inside of the patient body with stadium number 4, for example, by using this nuclear medicine imaging modality. And we cannot get that information only by using other types of imaging modality, right? So that is the importance of functional imaging. but we need to improve, of course, yeah, because if we just see it in 2 dimensions, especially this one, so there is a possibility that we can have a wrong estimation of the activity from this pixel value. Why? Because there is a possibility of the overlap organ, right? Because it's only 2-dimensional image. So therefore, we need to change it into tomography, not really change it, but I mean, there is a possibility to also use tomography. The principle is we measure all projection for all angle, and from this data, the spatial distribution of activity is reconstructed. So let's say that we have this 3-dimensional object, and then if we have a dot as 3-dimensional object, then we can actually rotate our gantry, our gamma camera head, to get a different projection from each of the angle. Then we can have many angles here, so that we can have in 3 dimensions of the image. Yeah. So that is SPEC actually. So what is SPEC? SPEC is single photon emission compute tomography. From the name itself, we can say that single photon. Single photon, it means that we working for the radionuclide that can produce a single photon. Emission, why? Because we have the source of the radiation from inside of the patient body, and then compute tomography, it means that we have it in 3 dimensions. So we rotate the gantry here. So basically, this one is just the gamma camera from the planar scintigraphy, right? But the difference is we rotate it. So if we have a source, I'm sorry. So if we have a source already inside of the patient body, so we're gonna have the radiation to all direction. So we rotate these 2 gantry of planar gamma camera head, and we can create a SPEC out of it. Okay. So again, SPEC is just a planar, but we rotate the planar to make it in 3 dimensions. And this is how it works. Yeah, you can see that this is the patient. You see that this illustration showing our gamma camera head is in opposite direction, right? But there is also a possibility that we can make this 2 gamma camera head in 90 degrees. Yeah, it depends on the protocol actually, whether you would like to do the protocol for the head or for the body and so on. So it's different protocol can be used. And then as you can see here, I'm sorry, the image is not very good actually here, but in general, you can see that we can really, this one is rotated. Yeah, so actually we can rotate it. We can see from different direction of the patient body. So what is the difference between the CT scan and SPEC CT? They are the same actually in the term of the acquisition of the data, because both of them are rotated. Yeah, the difference is if we're talking about the CT scan or X-ray, I think you heard about this before, right? CT scan is very famous. Most of the people know about this. So the difference is we have transmission radiation. It means that we have the source outside, and then from this source, we have this source creating radiation, passing through the patient body, and then we have a detector ring here that can detect the radiation. And then we rotate the source of the radiation and also the detector ring all together at the same time, yeah, to get all projection. For the SPEC, the mechanism are similar because we rotate the detector as well. But first, the difference is the location of the source are different. For this one, we have the location of the source is outside of the patient body because we have it here, and then we create radiation, and then yeah, the radiation will passing through this patient body. For this, no, we inject the radiation to the patient bloodstream, and then of course the patient body itself will become the source of the radiation. Yeah, and then we only have the detector actually, right? Located outside of the patient body. So there is no source. And then we can rotate it. Okay. So both of them are rotated, but yeah, the location of the source are different. Yeah. And then the next one is the positron emission tomography. So this one is for the radionuclide that can create a beta positive radiation. Where you see here, one of the example is for the F18. Yeah, we have F18, and then it will create a positron, and then this positron will move like this with a random path. At one point, it will lose the energy, and then it will meet this negative electron in some places, and the annihilation will happen. And then from this annihilation, we can see this annihilation back to back. Two gamma ray will be produced from this annihilation with an energy of 2 times of the energy of the electron mass. Yeah, and then we're gonna have this detector ring in this patient. Yeah? And as you can see here, we can read it in this red color. So the detector in red color will read the information from this radiation. Then we will read it with our computer, and we're gonna get this image in our computer. So this is the machine, yeah. And by the way, this one looks small because this is for the head, okay. But of course, if we have it for the body, then the this hole will be bigger. If we open it, then it is something like this. So basically, as you can see, yeah, the machine are similar with gamma camera, right? We have photomultiplier tube here. We have electronic here, yeah. We also have scintillator crystal here. The only difference between PET and planar or SPEC is that they don't have any collimator. Why? Because we have a back-to-back radiation of the gamma ray. Because of this back-to-back, then we don't need any collimator to define the location, because we already know that if this detector and this detector turn on because of this radiation, then we can directly tell the computer that the location of the radiation should be around this line. Yeah, this is what we call as the line of response. And this is the scintillator crystal. So there is a small difference with the one that we have from before, because we have this scintillator crystal cutter. Yeah, usually 8 by 8 here to make the resolution even higher. And for the photo multiplier, for one package of the scintillator crystal, we have 4 package of photo multiplier. And then we gonna have this electronic logic to see the information of the energy, the position, also the time for each of the radiation coming into this scintillator crystal. And then we can calculate then in the end the location in X and Z axis by calculating the signal received by the A, B, C, and D port here. This is one of the interesting video about that. Oh, there is no sound, I think, here. Oh, okay. Oh, okay, there is a sound. Can you hear it?
She's testing for cancer using a PET.
Yes, doctor.
Okay, thank you.
This syringe contains a radioactive form of glucose known as FDG. The doctor will soon inject its contents into her patient's arm, whom she's testing for cancer using a PET scanner. The FDG will quickly circulate through his body. If he has a tumor, cancer cells within it will take up a significant portion of the FDG, which will act as a beacon for the scanner. PET tracers such as FDG
are among the most remarkable tools in medical diagnostics, and their life begins in a particle accelerator just hours earlier. The particle accelerator in question is called a cyclotron, and it's often housed in a bunker within hospitals. It uses electromagnetic fields to propel charged particles like protons faster and faster along a spiraling path. When the protons reach their maximum speed, they shoot out onto a target. That contains a few milliliters of a type of water with a heavy form of oxygen called oxygen-18. When a proton slams into one of these heavier oxygen atoms, it kicks out another subatomic particle called a neutron. This impact turns oxygen-18 into fluorine-18, a radioactive isotope that can be detected on a PET scan. In a little under 2 hours, about half the fluorine will be gone due to radioactive decay, so the clock is ticking to get the scan done. So how can fluorine-18 be used to detect diseases? Radiochemists at the hospital can use a series of chemical reactions to attach the radioactive fluorine to different molecules, creating radiotracers. The identity of the tracer depends on what doctors want to observe. FDG is a common one because the rate at which cells consume glucose can signal the presence of cancer, the location of an infection, or the slowing brain function of dementia. The FDG is now ready for the patient's scan. When a radio-labeled tracer enters the body, it travels through the circulatory system and gets taken up by its target, whether that's a protein in the brain, cancer cells, or otherwise. Within a few minutes, a significant amount of the tracer has found its way to the target area, and the rest has cleared from circulation. Now the doctors can see their target using a PET, or positron emission tomography, scanner. The radiation that the tracer emits is what makes this possible. The isotopes used in PET decay by positron emission. Positrons are essentially electrons with positive charge. When emitted, a positron collides with an electron from another molecule in its surroundings. This causes a tiny nuclear reaction in which the mass of the two particles is converted into two high-energy photons, similar to X-rays, that shoot out in opposite directions. These photons will then impact an array of paired radiation detectors in the scanner walls. The software in the scanner uses those detectors to estimate where inside the body the collision occurred and create a 3D map of the tracer's distribution. PET scans can detect the spread of cancer before it can be spotted with other types of imaging. They're also revolutionizing the diagnosis of Alzheimer's disease by allowing doctors to see amyloid, the telltale protein buildup that otherwise couldn't be confirmed without an autopsy. Meanwhile, researchers are actively working to develop new tracers and expand the possibilities of what PET scans can be used for. But with all this talk of radiation and nuclear reactions inside the body, are these scans safe? Even though no amount of ionizing radiation is completely safe, the amount of radiation the body receives during a PET scan is actually quite low. One scan is comparable to what you're exposed to over 2 or 3 years from natural radioactive sources, like radon gas, or the amount a pilot would rack up from cosmic radiation after 20 to 30 transatlantic flights. Most patients feel that those risks are acceptable for the chance to diagnose and treat their illnesses. If you think scanning the human body is as fascinating as we do, check out this lesson.
So that is the first video. So we have another video here. It seems like there is no sound for this video, but basically the general mechanism are the same, yeah, for the video. So we have the patient. We would like to see what happened inside of the patient brain, for example. And then the next step is, of course, we need to see what we would like to see. One part of the patient brain. Then we already know what drug that we need. Okay, it is similar like, again, if you have a headache, then you need to go to the drugstore for the headache drug, right? And then the pharmacy department of the hospital need to create drug using the cyclotron. Yeah. And then after that, then we can change the stable nucleus to unstable one that can create a positron emission. And then, yeah, it's ready. So after we have the cyclotron creating the radioactive substance, then we perform the labeling, yeah, with what type of molecule that we would like to use. Depend again on the thing that we would like to see. So for example, we use here fluorodopa, and then we create the drug plus the radionuclide, the green one. And then we check the quality control to see that the drug is, stable and also pretty good, yeah, for the diagnosis. And then they need to be fast because the radiation half-life is very, very fast for the drug, for the radionuclide, sorry. And then after that, then we inject it to the patient body. And then this radiopharmaceutical drugs can help us to see, yeah, what happened inside of this patient brain. So the mechanism is we have this positron creating the positron, yeah, this radionuclide creating the positron, and then it will move, and after sometimes losing the energy and meet the electron to create an annihilation mechanism, which create also two different gamma ray back to back, almost 180 degree. And then these two gamma ray will move to the detector that we have here in our PET scan. And then we can detect the location by using this line of response mechanism. Then we're gonna have the image. Yeah, yeah. The green one is the one that having more radiopharmaceutical drugs compared to the other part of the patient brain. Then we can diagnose it. Okay. I think that's it. Yeah, yeah, we can check different diagnostic. Yeah. Okay. So, but we have some problem here for the PET scan, yeah, because not all the radiation can give us a good radiation. And then again, this is our job as a medical physicist to make sure that everything runs well for the PET scan, for the imaging, and so on. So this is some of the error that we can get from the PET scan. For example, the first one is the single. So let's say that we have a radiation here, yeah, from the annihilation phenomena. But then after it creates the line of response here, one radiation, we can use this detector to read it. So this detector can read this radiation, but this radiation is not working for the detector. So then we cannot get any data here, because how can we get the line of response if we have only one dot from the detector? This is what we would like to have. Okay, so this is the ideal phenomena that we would like to always have in our PET scanning mechanism. But the single can also happen, the scatter can also happen. So let's say that we have this annihilation here. We can create two different types of gamma ray from this annihilation phenomena back to back. The other one is going directly to the detector, but the other one, they have some mechanism here, yeah. They have some reaction with, I don't know, maybe other atoms or electron or etc. Then it deflects the path of the movement of this gamma ray. So what happened? So instead of using the detector around this area to get a good line of response, but it deflected, and the detector that turned on because of this radiation is located here. So therefore, the machine will read that, okay, the line of response is this one. So the source of the radiation should be around this line. And it's wrong, right? And then it is your job to fix this problem. Random mechanism can also happen where we have two different annihilation location. And then after that, these two can create this line of response of these two detectors. And you can imagine that this one is not nonsense, right? How can we tell the, the machine that the source of the radiation should be around this line? Because this is located outside of the patient body, but this error may happen. And again, this is your job, yeah, to fix the problem. And this one as well, because this triple can also make the machine confused, because at the same time they have two lines of response. The first line of response is this one, the second one is this one. Yeah, so it is confusing. Other types of error, for example, like the dead time correction should also be done with this single problem. Correction for random coincident, random also need to be done, but we can do it with the measurement. Attenuation correction also need to be done with extra measurement. Scatter correction and partial volume spillover is also needed to be solved. Yeah, and then again, no one can do this except you as a physicist with a physics background. Again, this can also show the importance of a physicist working in a hospital. And then we also have some different types of PET measurement, yeah, with the 2D and 3D. It means that there is also a possibility that for the PET, we have this collimator, yeah, and we can also remove the collimator if needed. If we use the 3D, then we have a larger number of coincidence line, yeah, factor of 5 to 7, larger scatter fraction, factor 2 to 3, and effective increase in sensitivity, factor 3 to 5. And then this is the, I think we already discussed about this. So you can see that the process and the mechanism of the functional information from cerebellum and striatum of this patient are different. Yeah, it means that we have more activity inside of the striatum part of the brain compared striatum. Yeah, striatum is more compared to the cerebellum. I'm sorry, the time is almost up, so I'll try to make it faster. So these are all the PET advantages. Yeah? For example, we can get the information of the quantitative image. We can get also to use the physiological nuclide. That this one is very good because in our body we also have some NO, yeah, and the human body won't make any problem with this because they are adapted very well to the biological system. And we also have this short half-life. This is also need to be considered, yeah, because you need to be fast. After you create the radiopharmaceutical drug, then you need to be fast for implementing it to the patient. And then collimation through coincidence, yeah, it means higher sensitivity, high gamma energy of 511. Of course, correspond to lower attenuation and also higher sensitivity and simpler attenuation correction. And these are several examples of the nuclide that we use. I'm sorry, I need to be faster. Yeah, I think it's better for us to get some minutes for our discussion. If you have a question, please let me know after this. So if we compare about the PET and SPEC, the sensitivity are different, a factor of 50 to 100. Yeah. Because we have collimation by coincidence, right? In SPEC, we have most of the time the collimator, and it is not good because we lost some signal because of this. And we also have detector rings for the PET, and more detector means more signal that you can get. Okay, we have shorter time scale measurable for the PET, so it's good also that we have a very vast measurement. And physiological nuclide, yeah. Then the biological system won't make any problem with the radiopharmaceutical drugs because it's already, I mean, adapted. The half-life are also one of the things that we need to thinking about, because the production near to the clinic for the PET, because the half-life is very, very short, and this radionuclide also can create this radiation exposure in a few millisievert. So it's quite hard. So you need to also check the accumulated exposure that the people get from the clinic to make sure that it is safe enough for them. And then the next one is the advantage of the spec is one of them is actually, for example, spec allows measurement at multiple energy when using different radionuclide in one step. So this is the PET-CD, one of the latest modality where we can have PET and CT all together in one machine. And actually we can also use this PET or spec for animals, So this is one of the example for the mouse. So we're gonna have a mouse, moving into this detector. It's interesting because by using this, you can imagine we don't have to kill the animal. We can have the animal lying down here, and then we can perform the measurement directly with only one animal, one mouse, and we don't have to kill it. But the problem is, this type of machine is very expensive. And for the image reconstruction itself, so we have analytical method and also iterative method. One of the example for the analytical method is filtered back projection. For the iterative method is the comparison of the forward projection of an initial estimation of an activity distribution with the measured projection and step-by-step improvement. So this is how it works for the analytical image reconstruction. So well, actually, you can imagine that this is the patient body. Let's say that we can define patient body with 3 by 3 pixel. But we don't know the number of the pixel value in priori, right? So therefore, we just combine the projection. So let's say that we have 1, 2, 3, 4 projection for different angle, and then we have this number, and then we filter it. So first we have this, and then we have the filtered one, and then we also do the filter for each of the projection, and then we can calculate it directly because you know that for x00, right? So x00 is related to A0 here, but A0 we divided into 3 columns, right? So it's A0 divided by 3. X00 is also related to B2 here, because this projection showing that x00 can be calculated from B2, but we divided by 3, and so on, so on, so on. So this is what we call as the analytical image reconstruction, and it's finished after one step. But a better one is iterative image reconstruction. Why? Because here we can do it iteratively to see the quality and to improve the quality for each of the iteration. So let's say that this is the number we have, right? And then we have this measurement. And then first of all, we use one projection. And then from this one projection, we just divide it into 3. And then we're going to have this. And then after that, we use the second projection to what do we call it? Subtract, this number 5. And we need to do it one by one. Subtraction means we add this information of this projection to the first iteration information. So we do this one by one, so the result will be much better after some iteration. But the problem is how many iterations. So based on the experiment, the number of the iteration is dependent on the aim. So if you would like to have a beautiful image, little noise and not quantitative, then 8 iterations is enough. But if you would like to have a quantitative image, then you need to have a very high number of the iteration. For example, you need it for the model, very noisy. So usually people in the hospital, they make a compromise. So they use around 100 iteration number, okay? And that's it for today's lecture, So this is the learning objective, hopefully that after this lecture, you can explain the basic component of the gamma camera and reproduce the term static and dynamic measurement, explain the term tomographic and describe the principle of SPEC and PET, discuss the differences between SPEC and PET, name the different method of image reconstruction and discuss their difference. And again, it is definitely not sufficient to just learn from this slide. Yeah, so actually I have several sources that you can use for the reading. Yeah. So for example, some journal, some society. Actually, you can just Google. It's pretty easy actually. The nuclear medicine community is pretty easy to find. For example, the Journal of Nuclear Medicine. Yeah, the European Journal of Nuclear Medicine. This one is from the United States of America. This one is from Europe, and this one is from Germany. And for the public authorities, you can also use IAEA. Yeah. And actually, you can find this online and free. So you can just Google IAEA Nuclear Medicine Physics book, then you can get it. So it's pretty good. The book is pretty good. So you can download it from their website, and you can read it if you are interested. And some additional free materials. So this is one example. By the way, I need to inform you about the attendance list. So I send you the link here in Zoom chat. So please fill it out. Okay. This is for your attendance. And then before we stop, oh yeah, by the way, do you have any question? Or maybe it is better for us to take one picture first before we go to the Q&A section. Yeah. So can you turn on your camera, please, for taking a picture together? Yeah. We are waiting. Only 2 students open their camera. Please, other student also open your camera. We just need to have one photo, and then after that we can turn off our camera again, because sometimes turning on the camera also can give some problem with the signal. Yeah. Okay. 5 more students, please turn on your camera. Yeah, Muhammad Aima, Siti Sahira. Please turn on your camera so that we can make it fast, because it's already 10 o'clock, by the way. Muhammad Aima and also Muhammad Haraf Takif, Siti Sahira. Hello. Now I start to wonder, maybe some of you doesn't really available. Okay, no problem then. We can take the picture now. Okay, 1, 2, 3. Okay, thank you. Because the organizer will check, yeah, the photo and also the attendance list. Okay, before we stop, is there any question from the student? No? Okay. Okay, so I think that's it for today's lecture. Enjoy the rest of the summer school and have a wonderful day. Bye-bye.
Thank you, Doctor.
Thank you.